Alright, in this video we are going to introduce the idea of representing straight lines using vectorial notation. The ultimate aim of this study is to be able to represent lines in 3D space using vectors. But we're going to start in 2D space or R2 because that is very familiar. And then the ideas we're going to have there, then we're going to extend them to 3D space. And the attractive thing with vector notation is that whatever formulas we're going to have in 2D, when we go to 3D space, they're going to remain exactly the same. We are just going to if we had like x, y, we're just going to add a z in our vectors, and then we have the formulas in 3D, and that's one of the convenient features of the vector formulation, is when you change from one dimension to the other, things don't complicate. Okay, so we're going to start with this straight line, y equals to 7 minus 2x. So I'm just going to do a rough sketch of this line here. So we know that the y-intercept is going to be 7, and it's going to have a gradient of 2. Okay, so this is going to be a 0, 7. Now when we want to write this in terms of vectors, we are basically going to look to construct a position vector. So that's a vector that starts from the origin. We are going to look to construct a position vector whose tip is always going to be along the straight line here. And we are going to construct this vector. It's going to be a sum of two vectors. Okay, so it's going to be one vector which is going to be a constant at any point on this line. That point on that line we are going to say its coordinates are x0, y0, and then that vector we're going to call it r0. So it's a position vector of the point x0, y0. Then we're going to add another vector which is going to be like basically along this line. Now this part of the vector is going to be variable. So when you add this vector and this vector, then the final vector we have is this one, which we're going to call r. Okay, so r is going to be the position vector of xy. So we want to construct this vector such that xy is always along this line here. Okay, r0 we can choose to be any point on this line. Okay, and then this second vector here is going to be determined by the gradient of this line. In fact, this vector here is what is called the direction vector, which I'll explain in a moment. Direction vector. This one, r0, is a constant vector. We can choose to be any point on the line. So let's talk about the direction vector. The gradient of this line, m, is equal to -2. From that we formulate the direction vector, because m equals to 2 says a horizontal displacement of 1 results in a vertical displacement of minus 2. So that's the meaning of gradient negative 2. Now this is already a vector because it's saying the x component is 1, the y component is 2. And so from that we write the direction vector 1, negative 2. So that's the vector that's going to go in there. But we want it to be variable. Sometimes we want it to be longer, sometimes we want it to be shorter, sometimes we want it to go the other way around, because we want to cover all the points on this line. So when it's like this long, then we've got that position vector, got that position vector, that position vector, etc. Okay, so this is going to be our direction vector for this line here, and indeed any other line with gradient of negative 2 is going to have exactly the same direction vector. Notice we can write 1, negative 2 here, we can write 2, negative 4. All these are the same direction vector, or if we want, we could do negative 1, 2. That's still the same. It's just that this one is going that way and this one is going the other way, but they are still representing exactly the same direction. So the way we do this, so the position vector of the straight line then is going to be xy. Okay, so xy, we denote r, which is the general position vector of the point xy. So we're going to write this as r0, which is the point we choose on this line. Then we are going to add a multiple of the direction vector, so t times m, where t is a real number. Actually t is called our parameter. So if for this line, for instance, if we choose r0 to be the point when x is 1, so when x is 1, y is going to be 5, so that's going to be 1, 5. So we can write then the equation of this line as xy is equals to 1, 5 plus t times 1, negative 2, where t is a real number. Then this thing is always going to give us a point along the straight line. By simply varying t, we're always going to have a point along the straight line. Okay, let's do a few examples. When t equals to 0, for instance, this thing is going to give us the vector, well, 1, 5, okay, which we know lies on that straight line. I'm just going to do integer values of t. When t is 1, it's going to be 1, 5 plus, so t is 1, it's going to be plus 1, negative 2. So this is going to be 2, 3. Okay, now you're going to find that if x is 2 here, y is going to be 3, because it's going to be 7 minus 4. So 2, 3 is on that line. If t is 2, then xy is going to be 1, 5 plus, I'm going to multiply this by 2, is going to be 2 minus 4 2 minus 4. So this is going to be 3, 1. And again, you'll find that that is on that line, because, okay, what this one is implying is that x is 1, y is 5. This one is implying that x is 2, y is 3. This one is implying that x is 3, y is 1. Okay, so this is our vector form of the equation of this straight line. Okay, so we can write it in an abridged version as follows: r. So r is just the position vector of a coordinate, general coordinate xy, equals to r naught, where r naught is 1, 5, then plus t m, where m is the position vector 1 minus 2. Okay, so that is our vectorial vector form of the equation of that straight line. Now from that we can actually extract something called the parametric form of the equation of that straight line, because we've got xy equals to 1, 5 plus t 1 minus 2. The x component of this is equals to 1 plus t. The y component is 5 minus 2t. So this is the vector form of the equation. This one is called the parametric form of the same equation. From the parametric form we can derive yet another form of the same equation called the symmetric form by eliminating t. So from the first equation, t is x minus 1. From the second equation, t is going to be 5 minus y all over 2. This one is called the symmetric form. Now, in fact, from the symmetric form, I think you're going to notice we can now recover the same equation we started with here. What's going on here? Same equation we started with here. So let's see how this works out. So if we multiply everything by 2, so I've got 2x minus 2, 5 minus y, bring y to this side, then this is going to be 5 plus 2 minus 2x. This is 7 minus 2x. So from that symmetric form we recover exactly the same equation that we started with. Just going to mention two things, and then we are going to generalize. The 0.15 we chose randomly, so choosing another point should not change the equation. Okay, so what this is saying is that this vector form can take different versions depending on which point we chose here. This one we could multiply by a non-zero constant again. So for instance, we could use -1, 2. Okay, so that means when the vector form of the equation is asked for, there is no one unique version of it. It can be so many versions, but the general guideline is that this point must be on the straight line. These vectors must be parallel. So that means these must be constant multiples of each other. So for now, for instance, suppose we decided to use the position vector of the y-intercept. So that means this is going to be 0, 7 here. Suppose we use the negative here. Let's see whether it's going to give us the same equation if we convert it to symmetric form. Okay, so in that case, actually, let's go for something different from the y-intercept. Let's go for when x is -1, this thing is going to be 9. So one of the points on this line is -1, 9. So let's go for that one as our R0. Okay, so we are going to write xy is -1, 9 plus, I'm going to call our parameter alpha this time, and instead of 1 minus 2, I'm going to go with -1, 2, which is just the negative of the one we used before. Now the parametric form now is going to be x equals to -1 minus alpha. Y is going to be 9 plus 2 alpha. So this is now going to be the parametric form. Then the symmetric form, if we make alpha the subject of the formula here, it's going to be -1 minus x. Make alpha the subject of the formula here, and y minus 9 all over 2. Okay, make y the subject of the formula, so this is now the symmetric form. Let's see if it's going to give us the same equation as before. We're going to have -2 minus 2x is equals to 1 y minus 9. Bring -9 to the left hand side. It's going to be 9 minus 2 is going to be 7 minus 2x equals to y, which recovers exactly the same equation as before. Okay, so let's generalize. Let's generalize. Okay, so here is a summary. So the equation of a straight line which goes through x0, y0 with direction vector. So that's from the gradient. So let's say the direction vector, let me use this. Say the direction vector is alpha beta. Okay, so then this is going to be given by xy is equals to x0, y0. So this is a point on the line. T is the parameter, and that's the direction vector. Compactly, this is R, this is R0, This is M. So that's going to be your vector form. Then if you take the x components, x is going to be x naught plus alpha t. Y is going to be y naught plus beta t. This is the parametric form. Then if we eliminate t from the parametric form, x minus x naught over alpha is equal to y minus y naught over beta. This is the symmetric form. Okay. In the next video, we're going to talk about something called the scalar form, and then we're going to do examples.